Hello, I'm Yaran Mane, PhD student in a group of Professor Luc de Raat at KU Leuven. And today I'll tell you a little bit about our research on soft-unification in deep probabilistic logic. Logic is a well-known and powerful way to express knowledge. Here we express that the Eiffel Tower is located in Paris. However, logic also has known limitations. For one, it is quite brittle. So we do not know, for example, that the Eiffel Tower is in Paris, because is in is a new and unknown relationship. Also restricted to using symbols and cannot use other representations such as images. One way to try and remedy this is soft-unification, where instead of using symbols, we use embeddings. So to compare the two terms displayed here, we will compare the symbol Eiffel Tower with the embedding of the image of the Eiffel Tower, and compare the embedding of Paris with the embedding of Brussels. This is similar to the idea of embeddings in knowledge graphs. This idea generalizes knowledge graph embeddings as we retain the full power of first-order logical reasoning. So what contributions do we make? In short, there are 2 points. Firstly, we give sound probabilistic semantics to learning with soft unification. Secondly, we also show that there is an equivalence of using soft unification with existing neurosymbolic frameworks, which are based on neural probabilistic facts, for example, DeepSoftLog. So how does this work? Learning embeddings inside of logics. Let's look at an example. When we query inside of logic, we have on the one hand a query, and on the other hand a program. So here, our query is whether this image is located in France. In our program, we have 3 rules saying that the Eiffel Tower is located in Paris, that Paris is located in France, and that located is transitive, meaning that if X is located in Y, this is the case also when X is located in Z and Z is located in Y. So now when we query, we can get proofs using SLD resolution. So when we first apply the first rule of our program, we equate the image to the symbol of Eiffel Tower using soft unification, and also soft unify the symbol of France with Paris. We can apply the same to the second rule. Here we only need to soft unify the image with Paris. Thirdly, we can get our intended proof by using the transitive rule, where we soft unify the image with the symbol of the Eiffel Tower. Evaluating such a formula to actual value is easy in Boolean logic. However, here, our soft unification will result in a numerical score, not in a Boolean value. Hence, we need to use a continuous generalization of logic. One way is to do this with fuzzy semantics, which was proposed by the neural theorem prover. Here, we replace the or and symbols by continuous functions, such as the maximum and minimum. Note that this makes our score, which results from a query, end-to-end differentiable. This means we can update our embeddings using regular training techniques such as gradient descent. There are some problems, however, with fuzzy semantics. For one, we get sparse gradients when we use Gödel semantics. Indeed, the maximum and minimum operations only give a gradient to one of their arguments, which means most parts of the formula will not receive gradients. More worryingly, we also suffer from local optima. Because of one proof being updated at a time, other proofs might not be discovered during training. There are fuzzy semantics which are not sparse, such as the product t-norm. However, then we make compromises on the semantics of our logic. We would like that equivalent logic formulas also give equivalent results, but this is not possible for fuzzy semantics that are not sparse. There are 2 other properties which are desirable to have when you have soft unification. One is that between 2 embedded symbols, there always exists a third one. This means our embedding space is connected. The other one is to avoid redundant soft unifications. What do I mean by this? Well, when you soft unify X with Y in a proof, it might be possible to insert a soft unification, so to unify X with Z and then Z with Y. When we say that there are no redundant soft unifications, we mean that these kind of insertions cannot improve the proof score. You can see this as a kind of triangle inequality on the embedding space. In our paper, we prove that these two properties are also mutually exclusive when we're using the good old T-norm semantics. So as a first contribution, we show that when we switch to probabilistic semantics, you can satisfy all of these properties. What does it mean to have probabilistic semantics? Well, in probabilistic semantics, we interpret the soft-unification as a probability. So in a way, you can see this as a distribution over formulas. And the probability that two symbols are equal in a randomly sampled formula is equal to the soft-unification score. Next, we also show that the soft-unification needs to take a certain functional form, namely as the exponential of a distance function. Next contribution, we show that soft-unification can be reduced to the uses of neural probabilistic facts, which is used by some other neurosymbolic frameworks. So in the example above, we have our example from before, which uses soft-unification. And now we can apply a source transformation, which makes a new program where there are no more soft-unifications, but now we insert probabilistic facts. So namely, in the heads of the rules, we replace the constants with variables, and then we add atoms in the body, which provide the probabilities of the soft-unifications. In the general case, this is a bit more complex. Namely, when you have nonlinear rules, these are rules when variables occur multiple times in the head of a rule. So for full details, we refer to the paper. We combine all of these ideas in a new neurosymbolic framework called DeepSoftLog. DeepSoftLog is an extension of ProbLog. ProbLog is a probabilistic logic programming language. So we extend ProbLog by adding embedded terms. Embedded terms are terms which are associated to an embedding. We note some differences with previous neurosymbolic frameworks. For one, the embedding of terms is optional. So we still retain and hence generalize the usage of normal symbols. Furthermore, we can not only embed constants, but also structured terms. These functors and structured terms can then be interpreted as functions which map embeddings into new embeddings, which can be implemented using neural networks. Thirdly, predicates cannot be embedded, but this is not an actual restriction and is easy to simulate. Lastly, our semantics is based on regular ProbLog, as discussed before. Let's look at some experiments. First, there's the knowledge graph experiments. Knowledge graphs are a large set of triples, or in logic also called binary facts. For example, here we express that France is a neighbor of Germany, Germany is located in Western Europe, etc. Then in DeepSoftLog, we can also add rules. Here we have a symmetric rule and a transitive rule. The rules contain dummy symbols, and during optimizations, we can not only learn the embeddings of the constants, such as France and Germany, but also these dummy symbols. So we can equate R1 and R2 to neighbor of to learn that neighbor of is symmetric. Similarly, we can use the last rule to learn that located is transitive. We show that DeepSoftLog considerably exceeds the performance of comparable neurosymbolic frameworks, such as the neural theorem prover, the greedy neuron theorem prover, and the conditional theorem prover. Lastly, we take a look at finite state machines. We can take a regular implementation of a finite state machine and replace the symbols of the states and transitions with embedded symbols. This means the finite state machine now becomes a differentiable model. Now we can learn the structure of the transitions by learning the embeddings of these. We can also learn the symbols. So for example, instead of learning from a regular examples, we can learn from sequences of images. So DeepSoftLog can jointly learn a perception network, which classifies the digits and the structure of the program, namely what transitions to take. Our results show that DeepSoftLog is more interpretable and also generalizes better compared to using a purely neural baseline. That was it. Thank you for watching. If you want to have more details, we recommend you to take a look at our paper. You can also find our code online if you want to try DeepSoftLog yourself. And if you want to have future updates about this kind of research, you can follow us on Twitter.